So after the last video, I was asked how can we say that the uncertainties are uncorrelated when we're using them to assume both a right-angled triangle and circular orbits. So the key thing to remember about some of these terms is that we approximate things when we have reason to believe that they're very similar, and we assume things when we can't solve it otherwise. So, for example, we make a lot of assumptions in quantum mechanics, where we assume that the perturbation is much smaller than the potential well that some particle sits in, because the problem is just too hard to solve otherwise. We can't solve the many-body problem. Here, we're simply seeing that sine law makes an unreasonably good approximation to just x equals sine theta when we're close to 90 degrees. Remember, firstly, that we previously explained that we can use these theta max measurements to determine the eccentricity of the orbits. It was from this eccentricity that we will measure that I stated because we get a low eccentricity for the orbit of Mercury, that we can approximate that orbit to have the properties of a circular orbit. In other words, we're able to approximate that sine law gives a trigonometric function. So we're not using uncertainties to assume anything. We're using observations and a bit of mathematics to show that something closely approximates another thing. I also previously stated that because it's an approximation, we can find out exactly how much we increase our uncertainty by. And since I've said this a couple times now, I'm just going to show you exactly how much we can expect this approximation to affect our answer. So what I have on the screen here right now is just me writing a bit of code to give us the orbits based on the eccentricities that we can measure. This is something that we find by looking at our theta max values over a long period of time. Then what I'm getting is the point along some orbit of Venus and finding the tangent line to that and where it intersects with Earth's orbit. This is when we would measure that theta max point for any point along Earth's orbit, and we're going to measure many of these in our experiment. What then is the angle between these two vectors from Venus? If we take the dot product of these vectors, we get the angle. I've gone through different points of Venus's orbit and found the angle it makes with Earth, and you can see that here. You can see that its variation is centered around 90 degrees. In fact, it has to be centered around 90 degrees by the definition of an ellipse, because the ellipse is going to have 2 points at least at 90 degrees. The variation about 90 degrees on this plot looks to be about 0.4 degrees or 0.8 degrees min to max. Let's call the difference 1 degree to make it easy to remember. Before we move on to the next step, I wanted to see what eccentricity we would need to get a variation of 10 degrees. If we go back to the eccentricity, we find that by playing around for a while, we have to multiply it by a power of 20 to get an eccentricity that gives us about 10 degrees of angular variation. Next, let's assess how well these angular variations allow us to use the approximation sine theta equals x. I'm going to use a Taylor series for this, and what we're going to find is that unlike regular functions, the error in a sine function will die off quadratically quickly. A Taylor series looks like this, and the basic premise is that you evaluate your function and its derivatives at a point you're interested in, and you can get arbitrarily close to the real function by adding infinitely many terms. However, if you notice, these terms of x minus a always increase in power as you go to higher terms. So if you evaluate your function close to a, these points are a fractional value to a large power, and so they die off very quickly. As well, if you cut off your Taylor series at some point, you can approximate your errors by looking only at the next term, because the term following will be another power smaller. Let's do this for our sine law function. The part we're interested in is 1 over sine phi. This is the part of sine law that we would use our 90-degree angles on. Doing this, we see that the first term is just 1, the second term happens to be 0, and the third term appears as a half times x minus a squared. This is a big part as to why I was saying this is a very good approximation to use. Notice if we use just the first term, we get exactly x equals sine theta, which is what we want to say we can approximate. So the Taylor series of sine law exactly gives x equals sine theta in the first term, and it has corrections in the following terms. Notice there's no linear term, which is a property of all trigonometric functions, and this means that our error will start to die off quadratically quickly, and the next term only exists as a power of the fourth. Remember, we saw the actual variation in phi should be around 0.8 degrees. However, as an example of how good this approximation works, let's instead take the case where the variation was 10 degrees. When you put in these numbers, you see the beauty of the approximation is that it's only 4% for a 10-degree variation. This is why I was trying to say before that we can use x equals sine theta. The error we gain in the quadratic term is minuscule. And remember, this was the error when we were using a 10-degree variation. What happens when we use the actual variation of 1 degree? Amazingly, it's 0.4% error, very small. This is quite a good approximation, and I hope you're satisfied with these errors. And if you're not, you'll be happy to know that I tricked you. It didn't actually square the values in this clip. And when I do this, you can see the errors are actually 0.4% error for the 10-degree variation and 0.004% error for the 1-degree variation. So to go back to your question, how can you say these uncertainties are uncorrelated when you use them to assume a right-angled triangle and circular orbit? What I want you to take away is that we use long-term measurements of theta max to see that there is a small eccentricity. If you're careful enough with your measurements, you can know exactly what this eccentricity is. When you know the eccentricity, you can find the variation in the actual angle, and you'll find it to be around 1 degree. 1 degree allows you to approximate sine theta equals x to 0.004%. Thus, our use of a right-angled triangle and circular orbits is not an assumption, but in fact a very, very, very good approximation.